Okay, welcome everybody to our joint NGTS and TFTC seminar today. Today we are pleased and honored to have Professor Asad Khattak with us. He'll talk to us about his latest research updates on the role of innovations in achieving sustainability. Dr. Khattak is a Beeman Distinguished Professor of Civil Environmental Engineering at the University of Tennessee, Knoxville. He has received his master's and PhD degrees in civil engineering from the Northwestern University, and he serves as editor of science for the Journal of Intelligent Transportation Systems. His research focuses on various types of innovations related to intelligent transportation technologies, transportation safety, and sustainable transportation. With all that said, thank you, Dr. Khattak, for being with us, and the floor is yours.
Thank you so much. I'm honored to wear the Michigan hat because this was given to me by Zach, who's online, and I am very happy to present to you on the role of innovations in achieving sustainability. And like you mentioned, one thing which I want to point out mainly to students is to publish in good high impact journals. And of course, Yafeng has been editor-in-chief of Part C, and these are the couple of journals that I'm editor of or associate editor of, and I want to encourage everyone to be, submitting good articles to these top journals that are certainly, peer-reviewed and are of good repute. So I just want to recognize all the sponsors over time that have contributed to the information that I'm presenting. I will try to present a picture and also rely on other studies and of course my own studies that were sponsored by these different agencies. We have currently the Collaborative Sciences Center for Road Safety, which is the National University Transportation Center, and I will be presenting quite a lot of research that we've done with them, as well as these other centers that have sponsored research, including EPA and university, and also the Energy Department, U.S. Department of Energy, and state DOTs. So the challenge of sustainability is first to be able to define it. And what typically people use are the economic, energy, and social aspects of our society. And basically, overlap between economic activity, enhancing that, but doing it in a green way where we have more sustainable systems, especially energy systems that are sustainable, especially the transportation systems that are sustainable, and also in terms of socially being able to have you provide access to all different groups, not just a few privileged groups. So it kind of encompasses the energy, equity, stewardship of our resources, natural as well as human-made resources. So that is kind of the basic idea. And, an optimistic view is that the demand on our environment, though, we see all these signs of, degradation of our environment, but it still can be met. These needs, human needs, can be met without reducing the capacity of our environment in terms of pollution and so on, to allow all the people to live well as now and in the future. Now, the sustainable pathways that people see, at least on the energy side, for example, will at least people are anticipating, scientists are anticipating that conventional oil, fossil fuels will be phasing out, although currently we are heavily dependent on them. But as you have seen in recent days, the price of oil has gone up very highly, and it all depends on very other political factors, and that creates our vulnerability to this source, which we want to overcome with more localized production of energy and also of economic activity, and bringing that into our system in a way that that supply chains are more smooth, and also in terms of social equity, that nobody's left behind. So the sustainability vision is to improve the efficiency and effectiveness of the transportation system by focusing on innovative strategies. What can we do to address energy, environment, equity, mobility, safety issues that we pointed out? So there are three pillars of sustainability that I would like to discuss today. One is the diffusion of intelligent transportation systems, automation and connected technologies in particular, more recently have been linking people, vehicles, infrastructure, and that helps a lot in achieving our mobility and safety aims. Also, urban development strategies like decreasing driving through smart growth strategies is very important, and also transition from petroleum fuel to alternative fuel sources. And there's more talk about decarbonization, whereby we depend less and less on the carbon-based fossil fuels. And this means adoption of alternative fuel vehicles, for example, hybrids and electric vehicles. And this whole thing, the good part and the optimism part is that we are able to now achieve some of our aims through large-scale big data, transfer of that data in very fast environments, and also through tools that are being developed and have been developed for transportation modeling, simulation, visualization. So that's the good part, where we can, I think, rely on some of the new tools that are being developed, especially AI. So I'll talk about that a little bit, but this just gives you the societal context and the opportunities. So as we know, safety is a huge issue. About $8 trillion in 10 years would be the economic and social costs of harm from crashes, wastage of fuel and congestion, and then fatalities. There are so many of them, and wide about 1.2 million people die every year. So these are huge costs that society pays. And then congestion and so on, economic cost of congestion. So all this turns out to be in a huge number, in trillions of dollars. But at the same time, the opportunities are to improve our supply chain efficiency, also improve mobility through these innovative strategies, as well as enhance safety, better air quality, enhance economic development. So the transportation system of the future, I mean, there's one concept of smart cities, which has been around for a while, but basically, this is the idea, and a kind of overarching idea, where you integrate automation and connectivity of vehicles, but also bring in electrification and freight efficiencies, as well as commute and travel efficiencies. So this is enabled by this computational power, like I was saying, but also ubiquity of ambient sensors, big data, artificial intelligence. So we'll talk about that a little bit more. And also, in terms of choices, we have a clear choice to continue to grow the way we are growing, sprawl out, single occupant vehicles, and that creates an environment that's probably not as clean as we would like it to be, as opposed to like local generation of energy, and then multimodal systems, and also people being able to walk and bicycle safely, as well as use public transit modes and share rides and so on. So those are that's a vision which is quite different from this vision, which is that of sprawl and development, as we have been doing in most cases. Okay, and so to advance the knowledge, we need to know how the societal goals of sustainability can be achieved by harnessing these innovations. And we need to be constantly producing that knowledge in order to improve safety and operations of the transportation system, focusing on transportation, for example, connected and automated vehicle technologies. I mentioned those, decreasing driving, smart growth strategies, and also transitioning to alternative fuel. So this is a conceptual framework which shows that there are some goals that we want to achieve, which are that of safety, mobility, accessibility, energy, and emissions. Now, typically we have policies in terms of like how we can achieve those goals. And then those policies, one example is the corporate average fuel efficiency standards. So those are policies that came into existence where the government said to automobile industry that every company can produce large cars, and also, but they have to produce kind of smaller cars in order to be able to meet a certain average fuel economy standard. So that's one example of a policy, and I'll show you what the benefits of those are based on some research that my colleague has done. But policy also, so policy has some goals, and policy also encourages certain actions like automation and connectivity, ITS, alternative fuel vehicles, smart growth, and all that happens within a context. The context can be defined by the transportation system, existing transportation system. Can it absorb that innovation? It also consists of the digital infrastructure. It also consists of now the alternative fuel vehicle infrastructure, for example, fast charging networks, or in other countries, CNG networks. So that's the context. But what we need are basically tools to achieve these aims and to be able to analyze and look into the future. So using this framework, I've tried to make this matrix so that we can focus our ideas on, okay, so safety. Well, maybe CAVs will have a large impact on safety. And then that we need to explore. But also we've explored, like, for example, Tesla produces electric vehicles, but are they really safe? And that maybe needs to be investigated further. We hope that they are safer than conventional vehicles, but we don't know fully. And also smart growth can improve safety, but we need to investigate some of that. In addition, smart growth will also improve mobility. That is, you will have multimodal mobility. People will have choices, not just auto-dependent. And similarly, the big impact of EVs obviously is on energy and emissions and environment. So, I'll discuss the tools that we can use for this in this framework. So the first one is that of CAVs, based on some of the reports that I've read from McKinsey and Company. There's like there are economic engines that can drive these innovations into the system, but yet is our system ready to receive these? And that's what is the question. But yet the benefits of these have been estimated at 850 billion per year once these systems start to diffuse more and more into our system. So as you all know, probably, 5 levels of automation that SAE has given us are increasingly getting the car to drive. But we are usually talking about these systems in the commercial market, and these are more like level 3 and 4 and 5 are very high-level systems that are being kind of tested, but they are not available at the moment, even though some car companies claim that they have like this autopilot, which seems like it's level 3 or 4, where pretty much the car is driving itself. Now, One other important thing that I want to mention is this degree of autonomy and cooperation. These are two things. Or you can have an autonomous unmanned military vehicle, or which doesn't talk to anything. It just, and in a desert or in a jungle, it can keep on navigating. But on the other hand, there is this cooperative systems where you have the collision warning system and so on, all the way to automated highway systems, which were worked on in the 90s by various companies as well as universities. And there was a demo in San Diego where they demonstrated the usefulness of them, but to implement them takes many more years. So what I'll try to do is to talk about maybe something in between, which has been, it's being tested, and it's being maybe closer implementation. So in order to proceed, I wanted to mention this idea of driving volatility, which is kind of an overarching concept. So if you think about it, let's say the speed is 10 miles per hour or meters per second or whatever the metric is, but the first one just shows that a car is going at a constant speed over time, right? The blue line. Now, which profile has more variation or more volatility? Well, obviously, the orange one has more volatility than the blue one, but the gray one is even more volatile, right? The car is braking harder and for longer periods of time, and then it's accelerating at more swiftly over periods of time and so on. So all that can be translated into different measures of volatility. I've mentioned a few of them here. You can do that for speed, for acceleration, for jerkiness or jerk as it's called, or even all the way for snap. These are the derivatives of speed, which different people use for various purposes in terms of improving the flow or smoothing out the flow. So standard deviation, just everybody knows that, but mean absolute deviation or time varying stochastic volatility, those are measures and shown here for different speeds, that these measures keep on increasing as the volatility increases. And that's an important concept. So volatility also captures crash risk, like safety, but also it can capture fuel economy. If you are accelerating hard and braking hard, then that means more fuel consumption. And also it can be a measure of flow stability. So it's basically deviation from the norm, and it's an indicator of mobility, safety, and energy and emissions, some of the key criteria. I'll come back to this in just a little bit to show you some of the results. But before that, the early evidence, which we are seeing for level 1 and 2 automation for forward collision warning system. I got this from IIHS, the Insurance Institute for Highway Safety, their website. It's all available, this information. And as you can see, forward collision warning systems already in real life situations, they are able to reduce the collisions of different types, collisions with injuries, with rear end crashes and so on, up to 44%. Similarly, with auto brake, it even is more 50% or so collisions are reduced, rear end especially. Similarly, lane departure warnings are showing good results here. Blind spot warning reductions pretty much in the 20%, 15 to 20% range, or maybe some 9-10%, but pretty high. And then rear automatic braking, where if you're reversing and so on, then it is able to brake, and that in addition, as you see, rear view cameras already are reducing backing crashes and so on. So this is an important aspect, that that is, this is already happening in the system, and we are seeing claims, insurance claims being used, and so on. And actually, insurance rates for cars that do have these systems are lower. So this is clear evidence that these systems are effective. Now, what we were trying to do is to look at the next level, and that next level is cooperative adaptive cruise control and adaptive cruise control is this, kind of, it's a combination of this thing. But it's basically safety, mobility, and energy and environmental benefits. We looked at that. And this paper was published with my students. And we've looked at the karma data to analyze how things will be in terms of cooperative adaptive cruise control, where the front vehicle communicates with all the vehicles in the back, as opposed to every vehicle having adaptive cruise control. And we looked at the kinematics of these cars in the platoons, and we looked at different measures like safety, time to collision, mobility, volatility measures, as I discussed, and energy and emissions as well. So there's clear evidence that when we have these systems, and this is karma data actually tested in the field. As you can see, speed is shown here for adaptive cruise control. So it's already different from conventional vehicles. And like we were saying, that's already 50% or so safe. But even more better is this profile over here of the same but the front car communicating with all the other vehicles that are following, so that you can see clearly that there's less variation here. And then similarly for acceleration and deceleration, that profile is very different from this profile. As you can see, this is for CACC, this is for ACC. So higher speed and acceleration, deceleration variation is observed with CC compared to the smoother flow of the following vehicles with CACC. And when you look at the benefits, we quantified all these benefits, looking at some of the volatility measures, which are based on speed. So as you can see, that too drops substantially. And when we compare that, these are measures of volatility in terms of stability in float, and that we see a 19% improvement, which ranges from 14 to 29, depending on which car it is, but that's the range, okay? And then for fuel consumption, we see that range is, you get better fuel consumption if you have less volatility or less acceleration, deceleration. So we found that is a 3.7% mean. It can vary from 0.5 to 6.7%, and emissions as well would be reduced, going to CACC from AC by about 3.74%. So this study pointed out that there are substantial benefits in addition to the benefits that we are getting from ACC. There are further benefits from CACC. And then as you keep on going, like I was showing you, you go to automated highway system, you're going to get even more benefits, okay? So that's a good sign. One other aspect that I wanted to mention was in our study, different study, we found that integrating AVs into the existing system is probably not so difficult. In fact, it might be interesting and easy to do it. So actually, A&M had collected some data, field data, and it's an interesting experiment. We analyzed the data. It's basically they used adaptive cruise control, and they looked at how human-driven vehicle that is manually driven is when it's following a profile of the leader that is like behaving like a conventional vehicle versus I guess non-conventional vehicle. So they took some profiles from a data set, NGSIM data set, and basically, they simulated that, but in one case it was driving more smoothly, in the other case it wasn't, and they did some experiments there. So scenario 1 was human-driven vehicle following a human-driven vehicle, and scenario 2 was human-driven vehicle following a level 1 AV speed profile. And basically, we found that there is lower driving volatility in terms of speed and acceleration, as shown here. That's like minus 18% lower. And then, acceleration volatility is even more further lower. And then time to collision is higher, as you can see. And then fuel consumption is lower over here. So by 11 to 4%. This is, like if you're following an automated vehicle, which is smoother, you will also tend to be smoother. So this will make it easier for these systems to be integrated into our system. Although initially we thought that, oh, well, I mean, it's unclear how these systems will be integrated. That is this automation. Now, that I'm not talking about high levels of automation, but at least the moderate levels of automation, it seems, are better for the entire system, not just themselves, but there are benefits to people who are conventional vehicles that are following these vehicles. Moving on to environmental issues, this is a big area. Of course, EPA is involved in some of the strategies for this. So as you know, I mean, our system is very highly multimodal, but basically for on-road vehicles, we are interested in seeing how smog and soot and also CO2 emissions, which to climate change and so on, are affecting our system. So we have about 29% of the greenhouse gas emissions are due to these emissions coming from transportation sources. And then this EPA website has a really good way of characterizing solutions. So it ranges from catalytic converters, which I guess are being stolen in California, from what I heard on the news the other day, because they have some good features inside, that is good metals inside. But anyways, there are a bunch of strategies you can do to improve this emissions, and some of them are maybe engine technologies and transmission technologies and diesel filters and so on. But we were wanting to focus more on better transportation planning and also alternative fuel vehicle technologies, which are critical. So one of my colleagues, and like I was mentioning to you, the policy is extremely important. He did study, Dr. Green. He used to work at Oak Ridge National Lab and now works at University of Tennessee. And, he's basically an expert on policy. And he looked at the miles per gallon improvements mentioned to you for the CAFE standards. And he says that we've saved since 1975, when these came into existence, these CAFE standards, because of the embargo, we've saved about $5 trillion and avoided about 17 tons of carbon dioxide being emitted into our atmosphere. And the reason he's saying is that if you see, this is the graph. The red line is for fuel consumption. Okay, and that has kind of remained stable. But our vehicle travel has been increasing. Okay, so it's been increasing substantially. So he's saying that gap between these two represents how much benefit we have gotten, basically, and that's this $5 trillion number when it's multiplied by the price of gasoline, and also you can put a price on CO2 emissions and so on. So So this is an interesting way to look at it and quantify the impacts of policy as over time, as shown in this paper. Another point, another colleagues in California have looked at how transient driving, that is aggressive driving and smooth driving, are different in terms of their CO2 emissions. So if you are going at speed 40, the emissions are much lower, as you can see, compared to this. This is the difference between if you drive aggressively versus not aggressively, almost twice as much. Okay, so they use what they call VSP, vehicle specific power, whereby you can calculate how much emissions you will get from the speed, acceleration, and also the vehicle's mass, which also captures the aerodynamic drag and also the different types of resistances that have to be overcome by the vehicle. So anyways, point is that smoother driving has huge implications for emissions, okay? And here's one of the studies that a student with me on looking at driving style. It was published in Part C. How aggressive or calm driving varies across different contexts in different neighborhoods. And also, can we use naturalistic connected vehicle data to classify these driving styles? So he decided to have at least three types of styles: calm, normal, and aggressive, okay, driving styles. And this would be obviously associated with the risk of crashes, more fuel consumption, more emissions. But that's an interesting aspect of this. So we started with data that has been collected in Ann Arbor, Michigan, and under SPMD. This was some time ago, but basically the collected basic safety message data, and we used that to process that data and look at different neighborhoods. So there were about 2,800 vehicles, and over 2-month period, we had data that had to be filtered and cleaned because it's a lot of data. And that's from Michigan. And then we divided the data into different neighborhoods that these cars had traveled in. And as you can see here, Amin worked on how to classify these different routes, which we had information about that the cars were traveling on, and in terms of highways, residential areas, and commercial areas. And then he used unsupervised learning techniques to come up with a classification of different driving styles, and then a driving score that we can give to people, and then they could potentially improve it. So we used the same idea of volatility, and basically, had to convert like speed into this volatility index over time. So these are temporal measures of volatility. And then he used clustering approach, k-medoids and k-means clustering. And we found that indeed, as expected, we classified people into aggressive, normal, and calm. And as you can see, with aggressive driving, of course, we observe that they have high speeds, and its acceleration and deceleration are higher, and as well as other measures of coefficient of variation of speed and acceleration are also higher. And as they become calmer, these measures become smoother and smoother in different neighborhoods. And then the driving, driver tracking and driver score, we used different methods for that. This is just some preliminary results for that, which show that aggressive drivers are they 1.76% of the time they are aggressive on highways, but on other kinds of roads it might be higher in commercial areas. So we basically looked at how we can have this kind of maybe a number for driving style, and then develop that for highways. It will be different, for local roads it will be different, but we can combine it. But I think we can have a driver score based on the data, and over time it can be improved, of course, with new data coming in. So basically we were able to do was to harness BSM data to classify different driving styles, and then driving style was based on this whole time-dependent variable of volatility. Used this unsupervised learning method to, and then used we can develop different thresholds for aggressive driving based on the data I showed you. And drivers were observed to be more aggressive on commercial streets due to more complex environments. Also, this driving score can be used to measure the overall driving performance, and it can be used in ADAS and also for proactively monitoring people who might be doing very aggressive driving most of the time in many environments. So then that's a problem. If it's just occasional, maybe it would be, it might not be that big of an issue, although it depends on what kind of an event it results in. In addition, we are also looking at biometrics of drivers themselves and trying to learn how we can use that data. So data on speed, we had this naturalistic driving study data, NDS, which has speed and acceleration. And also the interesting part is that it has distraction profile, like the person was looking at the front or distracted and looking at the side. All that we've used to extract the features and then use this deep neural network and so on to predict whether there will be an event will be baseline, which means there's nothing happened, but we just are monitoring people's speed for a random sample, as opposed to a crash or near crash. Okay. And this is just, due to time, I have to go through this fast, so I'll just refer you to the study to look at it. Has been published in Part C as well. Oh, sorry, AAP in a recent issue. Also, I want to mention Dr. Chakrabarty here at UT has been looking at some of the data for looking at edge cases, that is how AI will deal with cars that might be encountering new situations. So we looked at accident data in California Seville for AVs, and basically he used a Carla simulation to simulate those crashes that happened. But in this case, like, there is a car, this is the back view, this is, sorry, this is the front view, this is the back view. And then a person walks in front of the car and the car brakes and it's hit by another vehicle from the back. So these are LiDAR, I guess, camera and LiDAR images. And basically, he can then take these images and make them more like if it's raining or it's bad weather or torrential rain starts suddenly, how will these sensors behave? What kind of difficult situations we might encounter in this case? Okay, so I again will don't have too much time to go into all the details, but this is another piece of research that we are doing. So with that, I'll move to the smart growth. How am I doing on time? Ooh, okay. So I'll have to skip a few things. Basically, smart growth is another solution strategy. And in Hampton Roads area, we had a colleague and a former student who looked at this, and he basically said, what if in the future people were to settle in areas which are closer to roadways and more accessible and more compact, as opposed to being sprawled out? So he found that, as you can see, about 5% decline in VMT, NOx, VOx, and that's. But this model is not very sensitive to people changing their modes and so on. In addition, we looked at also traditional and conventional neighborhoods and travel behavior in those. So these defined by compact development, that is the neo-traditional neighborhoods are defined by compact developments and they're mixed use. That is, people can walk to the grocery store, and then they are also multimodal or better served by transit, ped, bike, as opposed to conventional neighborhoods which are unconnected and lollipop style. So here we try to collect for self-selection bias, which that is people who live in these neighborhoods might be self-selected. They may just enjoy walking, bicycling, so they resided here. So there's a kind of a statistical technique to correct for that. After correcting for it, we found that single family homes in living in neo-traditional developments make about 19% less automobile trips. And then they make more walking trips in that neighborhood, which is healthy. Okay, and then in terms of emissions, we looked at conditionality decision of driving versus not driving, and then given that you drive, how much emissions you have. And using some data, we looked at land use and how that connected with land use, and we found that balanced mix of uses, that is residential and commercial mixed together, is helpful. It has less emissions. Also, more connectivity shows that people living in those neighborhoods emit less. Okay. Also, we looked at Washington, D.C. area traditional transit-oriented development, and found that people do travel much more by transit in those neighborhoods, although their total trips are more or less the same, and but transit trips are more. So what I wanted to get to was this beautiful graph, which I've never published, but I think it's a very nice way of looking at it. So we did some studies in Virginia on university travel, which are dense environments, of course, and students and so on, having less accessibility to vehicles. They had like driving was much less in university neighborhoods. Transit-oriented developments, it's a little higher in neo-traditional neighborhoods, and then highest in about 89% in conventional neighborhoods. And then, as you can see, more walking, and it drops very systematically, and more transit in transit-oriented developments, as you can see, as you would expect. And that's what is interesting about this. So in general, balanced land uses and network connectivity are key to reductions in driving and emissions, and that all be seen as a positive for the environment. Okay, and then in terms of transformation to alternative fuel vehicles, you kind of go to bigger batteries, of course, compared to bigger engines, internal combustion engines, and this is a nice graph of how Dr. Green has did some studies, and you can get this information from fueleconomy.gov, which is a site maintained by our colleague at Oak Ridge National Lab. But basically, he's saying that hybrid vehicles, which have been around for quite 20 years, they have about 50% on average better miles per gallon, and the greenhouse gas emissions are 33% less. And that, we just don't have good information about these options, but their market share is about 6.5%. Their MSRP difference is about $1,700 from a conventional vehicle, and then the payback, that is, how long will it take for you to recover if the price of gasoline is $2.50 per gallon, and this is before they went to $7 in California, and you drive 15,000 miles, it will take about 3.7 years to recover the cost. Although now it may take just a few months, maybe, so that, and also there are environmental benefits, as you can see, the fuel economy improvement is about 50%, and then reductions are about 33%, okay. We are looking at this with one of my colleagues who works at Oak Ridge. We are looking at how to use National Household Travel Survey to see what kind of AFV impacts we may be able to analyze, and these early adopters of AVs, how AFVs, sorry, that might be contributing positively to the environment, of course, but we are looking at how those adoption decisions are made. This is just a paper that we've developed some time ago, looking at large-scale data, behavioral data, as well as more trajectories of vehicles. And there are these hierarchical models that we've estimated to try to understand how the relationships are between different, I guess, vehicle types, as well as, so this is fuel types, and then also the travel. So here are the key results, like the daily distances traveled are shorter for battery electric, plug-in hybrid electric vehicles. Drivers of BEVs, battery electric vehicles, make statistically significantly fewer trips, and they are calmer drivers versus gasoline vehicles. And this onion-shaped graph shows us how different cities, how in different cities we observed different levels of volatility in terms of measured as an acceleration, deceleration. So ultimately, we are trying to estimate now how ready we are for absorbing not just CAV technologies, but also electric vehicle technologies, and also changing our physical infrastructure, as well as in terms of public acceptance. So these are just results that I haven't even shared with TDOT, who is the sponsor of this study. This is just fresh stuff. So we find that actually, when we looked at it, the electric vehicle infrastructure actually rated pretty highly. So the closer you are to 3, the more prepared you are, based on a survey we did of state DOTs and also private sector partners and universities. And we found that, that is relatively good in terms of electric vehicle infrastructure here in Tennessee, but we are not so good on some of the other measures like digital infrastructure that is having CAV supported infrastructure, CV2X, for example. And then also in terms of physical infrastructure, we need changes in parking, for example, that is more friendly for CAVs and so on. That needs to be still done. And then I guess the digital also, we need to do improvements, and public knowledge is really lacking on many fronts, and we need to do a better job there as well. So just to summarize, we've seen that CAVs can impact safety goals, and like I said, we have substantial improvements in safety, up to 50%. I showed you based on IIHS data and some of the experiments that we are doing. There could be even further reductions. So these can be, that's a pretty optimistic picture of what we can do with CAV technologies. There's uncertainty about bandwidth and so on, band issues and so on, which I don't have time to go to, but nonetheless, these are important solutions. And then in terms of smart growth strategies, like we said, we see a very systematic increase in alternative mode usage, which means less emissions and less people maybe being exposed to to types of pollutants and while sitting in congestion. So that's this that's this mobility part where, but these smart growth can also have impacts on safety and energy and emissions. Of course, whatever is good for transportation, ability also good for emissions. Okay, and then the transition to alternative fuels, early adoption and use of AFVs showed you that hybrids have already contributed so much to huge savings to our economy in terms of like $5 trillion less in terms of emissions, and also better fuel economy. So increasing diffusion of these local energy generation and fossil fuels is going away from fossil fuel dependence is important. And the final thought is that we, try to put these pillars together. And this is thing that I would like my students and others to be challenged as to how do you connect all this together in a way that takes advantage of all of these. Now, just to give you an example, and maybe a version is Tesla. Tesla has done a good job integrating automation with their basic thing, which is electric vehicle. Okay, and they are obviously very, very successful industry leader in vehicle manufacturing. So in some sense, they have put together the pieces very nicely, and they are integrating them together. And the market is responding. Now, of course, it's for more moneyed people that can afford these cars right now, but over time, the price of these is coming down. And it seems like that would be the right strategy to follow, but more on a broader scale, where we can integrate not just electric vehicles, but also do mobility, look at mobility and so on, with this mass, which they call it. Let me see if I can. Yeah, this. I didn't go into the details of it, but this shared mobility is extremely important, I think. And we are looking at how that shared mobility, automation, connectivity, electrification, and shared mobility, how that can all come together. So I think that pretty much summarizes what I wanted to say. And we need to be able to constantly assess our readiness for absorbing these technologies and ingesting them. And I think we just have a lot of good work to do. So thank you. Appreciate it.
Thank you so much, Dr. Khattak, for your interesting presentation. And let's see if we have any questions from the audience. If you have any questions, please feel free to unmute yourself or type down your question in the chat section.
Hi, Dr. Khattak. I'm Alex. Interesting presentation. I'm really glad you mentioned smart growth and sort of changing our infrastructure in that sense, in terms of our development patterns. I'm curious, to what extent are some of these technologies sort of moving in opposite directions from each other? If we develop sort of infrastructure for autonomous vehicles, could that essentially push us away from smart growth and reducing our dependence on vehicles in general? So to what extent are they incompatible?
Yeah, that's $1 million question. One of my former students, Beth Shea, has been looking into this and seeing how the progress that has been made towards alternative modes be stymied by the this new need for infrastructure. for connected and automated vehicles. I think I see it more as complementary, though. Just like I was, we thought integrating automation into the system would be hard, but it seems like, others may be benefiting from it as well. And similarly, I wish I could show you a graph which may answer this question, but it's in a different presentation. So I'm going to try to get to that if I can. Let me see if I can stop sharing and reshare the screen, which has hopefully an answer to your question. So it's gonna take me a little time, I guess. So sorry, it's I can pull it. Yeah, I got it. So this graphic is going to show us a partial answer. So you see my screen, right? So Alex, this shows the we may need less infrastructure actually, because it's showing that automation can drive, to more green infrastructure. That is, you don't need that much capacity because these cars are all automated, and therefore we can reclaim of this this infrastructure back from this use by cars, because we drive farther from each other than an automated system, and we need traffic signals and so on at intersections, and they probably can do it without any traffic signals and stopping and so on. So does that answer a partial question that yes, there is some concern that we may be not heading in the direction of smart growth being kind of stymied by this need for infrastructure, but that need for infrastructure is going to be less, I think, rather than more. So in that sense, I see it as a positive, if that makes sense.
Yeah, I think I see that. And there's the million-dollar question of whether, switching to AVs, how that's going to affect people's choice of living location, like how far away they are from work. And that, I think, is going to play a big role as well. But we have no idea, essentially, on that one.
That is correct. And that needs to be investigated. And, I think it's a very pertinent research question as to, okay, now you have more automation, so it takes you less time and so on, and then do you really start moving away? We've seen some of this in a different way in the COVID case, when people started moving out of San Francisco, Los Angeles, and big cities, expensive cities, they just can work from home. So similarly, if they can keep on driving in these cars and keep working in the cars and sleeping in the cars, then maybe they'll even move out further. So, but that needs to be investigated, and we just don't have physically, like, a huge infrastructure right now for fully automated vehicles. So that question is more hypothetical at this point, but I think simulations can give us some insight.
Great. Thank you.
Thanks.
Thank you, Alex, for your question. Let's see if we have any other questions. So it seems like we don't have any further questions from the audience, Dr. Khattak. Thank you so much again for being with us, for your time, for your interesting presentation. And thank you everyone who joined us today. So have a wonderful rest of your day. See you again.
Thank you. Thank you, everyone. I enjoyed talking to you.
Thank you.
Bye-bye.
Bye.
Thank you, Dr. Khattak. It was good to see you.
Hi, P2. Good to see you.